Okay, this is the third video in our network flows series. There's one more video to come, which will just be example questions. So this is the last video which contains any theory. In this video, we're going to look at something called cuts, which is something that you apply to the network of capacities, not to the network of flows. Okay, so just be careful there. It's the network of capacities of the pipes. We cut the pipes such that we split all the nodes into two groups. We've got the source on one side, the sink on the other, and the cut value is the sum of all the pipe capacities that we've cut. So, for example, let's have a look at just cutting there. So what I've done is I've just sliced this network in two. We've got nodes S and A on the left-hand side of my cut line, and then nodes B, C, D, and T on the right-hand side. For a cut to be a valid cut, the source and the sink must be on opposite sides of the cut. They cannot be on the same side. And the reason why we do this is because it's kind of like taking this network and manipulating it in such a way that you are just considering these pipes that you've just cut, and the flow through this network has to flow through the sum of those pipes, because all of the flow is going from the source to the sink. So to get there, it has to pass all of these pipes. Now this network here is exactly the same as our original problem. All I've done is I've drawn it such that I've got my source and my A node on the left, and then I've got my other four nodes on the right, just so we can kind of really see that all the flow from the source to the sink has to pass through these three pipes in particular. So what is the source, what is the capacity of these three pipes? Well, A to C was 4, A to B was 2, and S to B was 5. So we've got 4 plus 2 plus 5 here. The maximum amount of flow I can push through this section of the network is 11. I can't push any more through it because, like I've said, all flow from the source to the sink has to pass through these three pipes, and the maximum value of these three pipes, maximum capacity in total, is 11. So we know that I cannot push more than 11 units of flow through this network because of this cut. Now I'm going to describe this cut as being cut alpha, and we tend to use alpha, beta, and gamma to represent cuts. But that's not the only place I could cut it. In fact, there are lots of different places I can cut this network. For example, I could cut it there instead. I'm going to call this cut beta. And what I've done now is I've just moved B from the sink side to the source side of my cut. So when I come to do the network, which again will look very similar to the one above, I've just done it so that we can clearly see that all of the flow from the source to the sink has to pass through these three arcs. I've got arc AC, arc BC, and arc BD. So if we look at the capacities of these three pipes, we'll be able to see how much flow we can push through this network. So A to C was 4, B to C was 6, and B to D was 3. So the maximum flow that I can get through these three pipes is 4 plus 6 plus 3. That's 13. So we know that the maximum flow through this network must be less than or equal to 13, but we already know it has to be less than or equal to 11, and that trumps it. So therefore we know that it has to be less than or equal to 11. Okay, so that's the idea of cuts and why we're doing it. It allows us to see kind of how much flow we can get through a network. But let's make one more cut before we go any further. I'm going to make a cut here. I'm going to call this cut gamma. So again, this is going to cross three arcs. Again, we can see that this cut has separated the source from the sink, so it's a valid cut. But let's have a look at what is going on here. So again, a very similar diagram. I've got the 4 nodes on my source side and the 2 nodes on my sink side. But I just want to look very carefully at the direction of these arcs. So C to T, that's this arc here, that has a capacity of 8. D to C has a capacity of 5, but that goes that way. And B to D has a capacity of 3, so that goes that way. So in this situation, even though I've got 3 pipes here, I don't really want to use this one, because this flow doesn't go from source to sink, it goes from sink to source, and I don't want that to happen. If I increase the flow in this pipe, it means I've got to compensate by increasing flow in these pipes to get it back over to the sink side again. So I really don't include that in my cut. So this cut is actually 3 plus 8, which is 11. So this actually equals the same as cut alpha. Okay, so cut gamma is not 16, which is a common mistake that students will make. It is a cut size of 11 because we do not count the 5. So what I'd recommend is when you are calculating a cut, just put a little circle around the arcs such that the arrow goes from source side to sink side, because that's the direction we want. We want the flow to go from source to sink, not from sink to source. So in the alpha cut, all 3 of those arrows go from source side to sink side. So 4 plus 2 plus 5, that gave us 11. With the beta cut, again, this one here, it goes from source side to sink side because the arrow is going that way. This one's going from source side to sink side, and this one's going from source side to sink side. So we include all 3 of those calculations in our cut calculation. So that's going to be a cut of 13, so 4 plus 6 plus 3. However, the red one, we're going to include that because it goes from source to sink side. We do not include that, but we do include that because, again, that goes from source to sink. So therefore, that's 8 plus 3, which is 11. We do not include this pipe because that is directionally going from sink to source. So that does not contribute towards the cut. Okay, and that's essentially cuts. So let's have a look at those down here. The way we notate these cuts is we use 2 sets. The set of nodes on the source side and the set of nodes on the sink side. So cut alpha can be denoted as SA, and then the other group would be BCDT. And you need to be familiar with this notation because you could be asked, find the value of cut, and then it will give you this in the text. And you need to know, okay, well that means that S and A are together, and then B, C, D, and T are together, so the cut goes there, okay? They won't always put it on the network for you, so just be aware of this notation. And the value of the cut, like I've said, is the sum of all the arcs which go from source to sink side. So that is 11 for cut alpha. Cut beta, that cuts SA and B off to the left, and then C, D, and T off to the right. So we would denote that as S, A, B in one set, and then squiggly bracket C, D, T in the other bracket. And we already calculated that at a cut value of 13. And then finally cut alpha, cut gamma, that cut D and T off on the sink side, and then A, B, C, and S on the source side. So that's S, A, B, and C on the source side, and then D and T on the sink side. And that had a cut value of 11, not 16. Okay, common mistake that students do make, but it is not 16 because a cut value, you only add arcs which go from source side to sink side. Okay, so let's have a look at a theorem. This is called the max flow min cut theorem. You do not need to be able to prove it. You do not need to know the proof of it. You just need to know that it is true. and you need to use the max flow min cut theorem to justify a maximum flow through a network. So it is clear that there does not exist a flow greater than any valid cut, okay, and that is for this reason here, kind of pinching the network together. We cannot get a flow that's bigger than 11 through this network because of this pinch. Okay, so it is clear that there does not exist a flow greater than any valid cut. But conversely, there does not exist a cut less than any valid flow for the converse of this kind of picture. If we have a flow through a network, there's nowhere to pinch it such that you've got less than that flow going through it. So that is also a true statement and hopefully fairly obvious to you. What is not necessarily obvious, which is the actual theorem, moreover, the smallest cut value will equal the largest flow value. Okay. The smallest cut value will equal the largest flow value. And this idea is the max flow min cut theorem. So when you're answering a question, if it says justify why this is a maximum flow, you could say, well, this cut is such and such, which equals this flow. By the max flow min cut theorem, this must be the maximum flow through the network. Okay, so that's how we tend to use it on this course. Okay, we don't tend to find every single cut value because there are just too many of them. It's exhaustive. But if you find a cut value that equals a flow value, then by the max flow min cut theorem, they must be the maximum flow and the minimum cut. Okay, simple as that. Right, so let's have a look at this network. This is a network that is that we looked at in the first video. And we're just going to have a look at these cut values. So if you recall the first video, we found that we found a flow through this network that was 210 units. Let's see if any of these cuts sum to 210. Okay, so cut alpha, that is just the sum of these three, and they all go in the right direction. They all go from source to sink. So the value of this is 100 plus 60 is 160 plus 120. So that is 280. So the value of cut alpha is 280. Excellent. Okay, cut beta. This one, that's fine. That's going from source to sink. This one's going from source to sink, so that's fine. Okay, sink's on the right, source is on the left. This one's going from source to sink. This one's going from source to sink. This one we're not going to include because this arc, CB, has an arrow going up, which means that is going from sink to source side. So we don't want to include that in our cut calculation. And what you'll tend to find is if a question asks you to calculate two different cuts, one of them, all of the arcs will go from source to sink, and the second one, there'll be one or more that go from sink to source, just to try and trick you, or try and make sure you're paying attention rather than trick you. Okay. And then this final arc we want to include because that goes from source to sink side. So we're going to sum these ones together. So 120 plus 30 is 150, plus 40 is 190, plus 25 is 215, and then plus 120 is 335. So the value of cut beta is 335, not 375. Okay, and finally, cut gamma. Is going to be this, these four, so they all go in the right directions, they're all going from source to sink. There we go. I did allude to this idea when I did the video earlier, 2 videos ago. And we couldn't push any more flow through because these 4 were saturated. So we've got 90 plus 40 is 130, plus 10 is 140, plus 70 is 210. So cut gamma is 210. So from the previous video, the flow through the network was 210 that we found, and that was equal to a 90 going that way, a 90 over there, a 90 across there, 40 up there, might not be exactly this actually, but this is a solution. 0, 0, 50, 0, 70, 10, 0, 70, 10, and 0. Okay, so this is a solution to the problem, which is how much flow can we get from the source to the sink through this network. Might be slightly different to the 2 videos ago, but it doesn't matter for this this part of the video. And what I'm going to do is going to highlight which of these pipes are saturated, which of them are at their maximum capacity. So we've got the 90, that is saturated. This 90 here, that's got a pipe capacity of 120, so that's not. There's a 90 here, but that's got a pipe capacity of 100, so that's not. There's no flow through those, so they're not saturated. 50, but that had a capacity of 60, so that one's not. 40, that one had a capacity of 40, so therefore that is saturated. This one's 40 as well, but that had a capacity of 50, so that's fine. There's no flow through there. 80 there, but capacity of 120, so not saturated. 10 through there. 10 is the capacity, so therefore that is saturated. And then 70 there, and that was its capacity, so therefore that one's saturated. Those two are 0, and then we've got a 70 here, but the capacity was 120. So those are the 4 pipes that are saturated. There's no more saturated pipes in this solution, but what you may notice is that gamma was chosen as going through those 4 pipes. So that was the definition of gamma at the top of this page. And what you'll find is the minimum cut will go through saturated pipes of the maximum flow. It won't go through any other pipes unless the direction of those pipes is only sink to source. Okay. So when you're dealing with a problem which contains a cut, you know that the minimum cut will only go through saturated pipes of the maximum flow or pipes with no flow from sink side to source side. Okay, so if this pipe was saturated, for example, then I could pass through, if this pipe was saturated, I could pass through here as a cut, and that would be a minimum cut because this goes from sink side to source side, so that wouldn't contribute towards the cut. So therefore I can pass through that arc without saturating the pipe. Okay, so that's quite a useful idea. If you're told which pipes are saturated, for example, and you need the cut, you can start there. Okay. All right. One other quick example I want to consider is this cut. I've called it cut alpha on this network, as we have not seen this network before, and we won't see it again. It is only for this illustration. And I've just written down its definition here in kind of set notation. So we've got S, A, B, C, and E, okay, on the left-hand side, or the source side of the cut, and then D, F, and T on the sink side of the cut. Okay, so let's just have a look at all of the arcs which go from source to sink. So there's that one, which goes from source to sink, so we're going to include that. That goes from source to sink. That goes from source to sink. Oh, sorry, no, that goes from sink to source. I'm not going to include that. Not going to include that. That goes from source to sink. That goes from source to sink. That goes from source to sink. That's source to sink. And that's source to sink. So let's sum those up. We've got 40, not including those two because they go from sink to source. 50, 60, plus another 50 is 110, plus 40 is 150, plus 10 is 160, plus 50 is 210. So one could argue that this cut is 210. However, if you did argue that, you would be wrong. I'm going to give you just a couple of seconds, or you can pause the video just to see if you can see why that might be an incorrect answer in this case. Okay, the answer to this problem, why this is not a correct value for this cut, is because let's just consider this arc here, DF. This arc has crossed the cut line twice. What's important to note is this does not go from source side to sink side at all. It goes from sink side to sink side. So yes, we've ignored the 40 here, but we've included the 40 here when we shouldn't have done, because we don't want flow going from source to source from sink to sink to count towards the cut value. So just to illustrate this further, what I've done is I've just drawn out exactly the same network again, but this time I've omitted the arc length DF. And what I'm going to do is I'm going to draw this arc in a different position. So it went from D to F, it had a capacity of 40. So instead of going straight there, I'm going to go round here, which is completely valid. It's isomorphic. It's topologically equivalent to the one above. There's nothing I'm doing there to cheat the system. But we can see that this arc now no longer crosses that cut at all. And that just makes it a little bit clearer. So really what you're looking for is not the arc direction to go from source to sink. What you're really looking for is a node going on the source side to a node on the sink side. And it can't go from source to source, it can't go from sink to sink, and it can't go from sink to source. Got to go from source to sink. So with that in mind, this is now valid because that is source to sink side. This arc here is also valid, is not valid because that goes from sink to source side. This one is valid, this one is valid, this one is valid, and this one is valid. So those are the ones that we are going to sum to calculate the value of this cut. So that's 40, ignore that, 50, 60, 110, 120, 170. So the actual cut value is 170. Okay, going back to this one here, when you got to this one, you should just look, oh, okay, this, yeah, the arrow goes from source side to sink side, but actually the node is sink side to sink side. So I don't include it in my cut. The node at the beginning of the arrow must be on the source side, and the node at the end of the arrow must be on the sink side. Okay, that's all I want to do for cuts and the min cut max flow theorem. We'll see that in action a little bit in the next video. One other thing I will say is I've not looked at any networks which don't have non-directed arcs. If you are looking for a cut in a network which doesn't contain directed arcs, then you count it because the flow could be in either direction in that pipe. So you would count a non-directed arc, okay, as an arc with no arrow on it in a cut calculation, okay, provided there's one node on the source side and one node on the sink side. All right, if you have any further questions, please just pop a comment in the bottom and I'll get back to you when I can. Thank you very much for watching.